Okay, welcome back everyone. In this video, we're going to be taking a look at a very important concept, Gauss's law of gravity. And we're going to look at how this springs from what we did last time, showing that all the mass of an object can be thought of as concentrated at its center. So we're going to jump right into this, but we saw that the force of gravity is concentrated at the center of a spherical object. And this leads us to Gauss's law, which is that the gravitational flux through any closed surface is proportional to the enclosed mass inside of that surface. Okay, well, let's back up a second. What is gravitational flux? Well, flux is a very important idea in physics, and we'll study it with electric and magnetic fields as well. But here is a picture of a mass and a gravitational field. And the gravitational flux is defined conceptually as a measure of the number of gravitational field lines passing through this closed surface, which might be the red circle. Okay, now a closed surface could be a circle, it could be a sphere. Well, it can't be a circle if it's a closed surface. It would have to be a sphere or like a cylindrical can or a box. Okay, but it has to have a surface area. Okay, so in lots of cases, there's a spherical geometry that makes the math a lot easier. And so here is the equation, and we're going to break it down. Okay, so this says that the surface integral of g dot dA is equal to negative 4 pi times big G times the mass enclosed, which is equal to what we call the gravitational flux. Okay? So, and this is the mass which is enclosed by a surface. And we're going to break this down a little bit more. Okay? So, first of all, here is our basic equation. And we're going to break down this symbol first. This is what we call a closed surface integral. So instead of integrating in a straight line, we think of this as integrating everywhere on a two-dimensional surface. G dot dA is the dot product of the gravitational field with dA, which is a unit area vector. And if the surface is a sphere, dA will point outwards. So one way to think about this is that a small part of a sphere might be like this, which has a dx and a dy. But together, we say that it has a dA. And this thing has an area vector. Okay? We call that area vector dA, which is perpendicular to that surface there. And we write that dA is actually equal to the magnitude, which is the area itself, times n hat. And n hat is a unit vector in the perpendicular direction to a surface. Okay. So, for example, if we have our picture here and we put a surface, we can see that the unit vector on that surface would be going outwards like this, perpendicular there. Okay? So you might notice that we have a negative sign here in Gauss's law, and this negative sign is going to account for the fact that when we do this surface integral, that G is going to be pointing inwards and dA will be pointing outwards. So we'll get a negative sign from that dot product. And negative 4 pi G times the mass enclosed is a constant, but it shows that when you take the dot product of G and dA over the entire surface, the result only depends on the mass enclosed within that surface. Okay, so let's do an example. Right? Let's use Gauss's law of gravity to show that the force of gravity is, in fact, negative g m1 m2 over r squared in the r hat direction. Okay, so let's do this. Let's take a planet here, m1, and another one M2. Okay, and let's draw what we call a Gaussian surface. And this is a sphere which is surrounding M1. And basically what we're going to do is we're going to show that the force of gravity is going to be equal to M2 times G, the gravitational field. So what we're trying to do is to solve Gauss's law for the value of the gravitational field. Okay? Now we know that the surface integral of this gravitational field dotted with dA is equal to negative 4 pi big G times the mass enclosed. Okay, so one thing that we can do is we can note that at any point on this surface, G will be pointing inwards, but dA will be pointing outwards. So basically the integral of G dot dA is going to be equal to the surface integral of just G times dA. We can take away that dot product. And if you like, there's probably a negative sign lurking there, but I'm just going to leave that for now. And that's equal to 4 pi times big G times the mass enclosed by this Gaussian surface, which is just M1. M2 is not inside of that surface. Okay, now this is going to turn into G times the integral of dA. And the reason that we can pull the G out is that G is constant on the surface of the sphere, and also so is dA for that matter. Okay, and that's going to equal negative 4 pi G M1. Okay, now this expression here, the integral of dA, is also known as just A, the surface area. So G times A is negative 4 pi big G M1. So this means that the gravitational field G is equal to negative 4 pi G M1 over A. Okay, now what is the surface area of a sphere? That's right, it's just 4 pi r squared. So those 4 pi's are gone, and that's why 4 pi shows up in the first place. And we get negative G M1 over r squared. And at this point we're done, because the force of gravity is just M2 times G, so it's just M2 times negative G M1 over r squared, which is what we set out to find. So this is a proof that Gauss's law of gravity actually works to give us the correct value. Okay, so now let's do one more example problem, which is going to be a little bit more involved. And for this one, we want to find out what's the force of gravity, Fg, as a function of this mass's distance from the center of the Earth. So we're going to assume that the Earth has a constant density. Okay? Now to get the force of gravity, again, our plan is going to be Fg is going to be equal to m times g. So we need to find little g first. And we'll do that using Gauss's law. So the integral of g dot dA is equal to negative 4 pi g mass enclosed. Okay? Now, in this diagram, there's a circle that's drawn here. Okay, and this is going to be our Gaussian surface. And this Gaussian surface is not going to enclose the entire mass of the Earth. It's going to enclose, so M enclosed for this will be capital M here, which is not the entire mass of the Earth. Whoops, it's only a portion. So we need to set up some sort of a ratio. And we recognize that the density of the Earth is the total mass of the Earth over its total volume, which is also equal to the mass enclosed divided by the volume enclosed. Okay, so we can say that the mass enclosed in this expression is going to be the mass of the Earth times the volume enclosed over the volume of the Earth, which is the mass of the Earth times, okay, now this is a sphere, okay, so the volume of a sphere is going to be 4/3 pi, and then this is going to be little r cubed, and that's the volume that's enclosed within this intersection. And the volume of the Earth will be 4/3 pi radius of the Earth cubed. So the 4/3 pi is going to cancel, and that's going to give us that our mass enclosed is going to be equal to the mass of the Earth times little r cubed over radius of the Earth cubed. And that makes sense because when we're at the surface of the Earth, r is equal to re at the surface, and mass enclosed is just equal to mass of the Earth. Okay, now let's take this result and plug this in for the enclosed mass here, and let's evaluate Gauss's law. Now, like before, everything that we did in the prior example was true, so the integral of g dot dA turns into g times the integral of dA, and that's equal to -4 pi g times mass enclosed, which is mass of the Earth, times little r cubed over big R cubed, radius of the Earth cubed. And we can also say that the integral of dA is 4 pi times little r squared, because this is the area of the Gaussian surface, not of the entire Earth, but just of this Gaussian surface that we've chosen. That is equal to -4 pi g mass of the Earth times little r cubed over big R cubed. Okay, and so the 4 pi is going to cancel, and this r squared will cancel that cube. So what we're left with is that g is equal to -g mass of the Earth times r over radius of the Earth cubed. Okay, and that means that the force is going to be -g little m mass of the Earth times r over radius of the Earth cubed. Okay, now ignoring the negative sign, just looking at the magnitude of this force, what does this say? This says that as r increases, the force of gravity actually increases linearly until you get to a maximum value. Okay, and so this portion of the graph is proportional to r to the first. Then, when we hit the surface of the Earth, we turn into our normal 1 over r squared, because we have now gained all the mass that we can, and the force of gravity will just be gmm over r squared. Okay, so this is very important, and so this value here where it switches over is the radius of the Earth. Okay, but the last thing that I want to point out is that notice that in all of this we've been dividing by an area which is 4 pi r squared, and that's important because this force, which is proportional to 1 over r squared, really tells us about the density of the field lines, and that density of the field lines is inversely proportional to the area that they pass through, which sort of goes as r squared. So at 1r you have an area of r squared, and at 2r you have an area of 4r squared, and so on. So really what's happening is that even though the number of field lines is staying constant based off the mass producing that field, the density of those lines is getting less, and that tells us that the field is decreasing in strength, because the strength of the field can be thought of as the density of the lines. And here's something kind of wild. The fact that we have 1 over r squared force laws is because we live in a 3D universe, and the surface area of a sphere is 4 pi r squared. And so I'm going to leave you with that thought, and next time we will wrap up our unit on gravity by talking briefly about black holes.